Hello students, welcome to series of lectures on digital speech processing. In this video you will be able to learn the concept called parametric representation of the speech. In the previous video we have already seen what is the basic pattern recognition approach as part of automatic speech recognition. Okay. Now in this video you will be able to learn the topic of parametric representation of the speech, and we will also solve some of the problems. Okay, because in the evaluation process we need to calculate what is the word error rate. So that is also very important parameter we need to evaluate. Okay, that shows how much of utterances that we have selected, and the same thing that we are going to be taken into consideration into the listener side. Okay, let's get started. So on completion of this lecture, you will be able to understand the parametric representation of the speech. And this is an introduction of an ASR we have already seen in the previous. The main goal of ASR is to convert from speech signal to the text. Okay, so these are the steps actually we need to follow. That is data acquisition, the first one, and then pre-processing, and then feature extraction with the help of the MFCC. Okay, so in this unit anyway, we are going to be learning the concept of MEL frequency substrate coefficients also, that we can see. Now after that, acoustic modeling we need to build up, and with the help of HMM, hidden Markov model, we are taking the help to design the model acoustic, and then we will be having the language model. Okay, so these two are the statistical models. Okay, so we need to build a statistical model of the likelihood of the word sequences in the language being recognized. So here, how much of words correctly we are getting, so that purpose we need to do the evaluation, and after this we will be having the decoding. Okay, so we need to use these two models, acoustic and the language models, to decode the speech signal and to determine the most likely sequence of the words that corresponds to the input of the speech spoken by the speaker. Okay, next is the evaluation. So we need to measure the performance. Okay, whether we are getting the same words when you take the different utterances of the speech. Okay, so for instance, if you record a sentence and it is consisting of 5 words, okay, let us consider like that. That means all the 5 words we need to correctly understand by the machine, and the same thing should be reproduced onto the text. Okay, so that is what. So for that we will be doing some evaluation process. Okay, that is a word error rate is a very important performance evaluation measurement. Okay, that also we can see in this PPT. Alright, so this is the traditional pattern recognition model for the speech recognition. This we have already seen in the previous video also. After recording the speech, that can be given to the feature extraction. The one point you need to remember, so when you recorded a speech, that means we are going to be having, it is involved in the process of the framing, windowing, and the parameterization, the methods of time domain parameters we are going to be evaluating from the each and every frame. Okay, everything that we are going to be doing, pre-processing. Right, and then feature extraction, so with the help of MFCC. So in place of this block you can also visualize MEL frequency substrate coefficients we need to consider, so that also we are taken into consideration in this. And this is a test template. Okay, so this template, this feature vectors are going to be compared with already reference template which is already there in the machine. So this is a pattern matching. If the same test template is matches with the reference template of the ASR, then we are going to be taking the decision rule that is the correct word and that the recognized text can be available. So this is a block diagram. This is a flow. Actually, we know how we need to record a video. How we need to record the speech signal, and then that can be doing some analysis point of it. Now, so what is the goal of the speech recognition? Okay, this also we clearly mentioned in the first slide of this ASR. The main goal of an ASR is that to convert the spoken utterances into the text. Okay, so after recording a speech signal, that we are dividing that into frames, and each and every frame should be converted into the text with the help of the ASR, that is automated speech recognition. This is what. Now, so this is a stage.
The first stage, speech to text converter converts the input speech into corresponding text. For example, the input speech, "Will you please help me?" is recognized by automatic speech recognition system and text for it.
So this is the sentence I have taken as, "Will you please help me?" Okay. So when you take the English speech, when you give that to the automatic speech recognition, that English text will comes out. Okay. So you can also, I hope you also hear the voice of the speaker. Okay, so how we need to use this kind of the stage.
The first step involved in speech recognition is to perform endpoint detection. The spectral shaping and endpoint detection algorithm performed on the input speech separates the individual words from the original and isolated words are obtained.
Again, so in this slide what we are doing is that the continuous speech input we are taken into consideration. Now if you use the endpoint detection, because this endpoint detection algorithm will helps us. Okay, so what is the speech read, what is the starting point of the utterance, what is the end point of the utterance. Okay, so that means it is a discrimination of silence and then voice and then unvoiced signal. So that is the way how we are going to be using this endpoint detection. Okay, once you take the continuous speech input and we are taken into consideration that the output is isolated words. That is, in the previous slide that we have seen that the speaker is speaking, will you please help me. Okay, so total 5 words which are there in a sentence. So those 5 words we are going to be doing as an isolated words. Will you please help me, like that. Okay, now listen to the next slide.
As the speech signal changes very slowly with respect to time, the endpoint detection algorithm involves the two parameters, that is, short time energy measure and the short time zero crossing rate, which decides the start and the end of utterance of each word in the speech signal. Thus, isolated words are obtained from original speech signal.
That is what. So this we have already seen in the unit number 1. Okay, so endpoint detection algorithm. So what we are doing is that we are taking the short time speeches or speech utterances. Okay, so those we are calling as the short time energy, and there are so many other time domain methods are available to evaluate these kind of things. Okay, so normally what we are doing is that, so we need to decide what is the starting and end of an uttered word. Okay, and out of the box is not our interest. Only we are going to be making, we need to ensure what is the utterance that is coming from the sentence, and that we are going to be picking. That is only our interest. That is what the speaker is telling.
Here we have obtained the results for the endpoint detection algorithm implementation. The input speech signal, will you please help me, is converted into 5 individual signals which are isolated words.
Alright. So will you please help me? These are the results actually when you apply any kind of the method in the MATLAB. You will be getting the speech signal like this, and this is the actual sentence which is spoken by the speaker. Will you please help me? Now when you take the will, this is an isolated. Will you please help me? These are the isolated words. Okay. So this is the way how we are going to be achieving the results of isolated words formation.
Once endpoint detection algorithm is performed, the pure speech signal is then divided into number of frames, and windowing is performed using Hamming window for each frame, and then the discrete Fourier transform of each frame is found out. On the spectral graph, frequency scale is divided into Bach scale subbands, and the speech vector is formed for each frame computed by summing up amplitude of all frequency components in each subband.
Alright, so I hope you listen the words of the speaker. So in the step 1, what we have done, that's the endpoint detection algorithm we have used. After performing that stage, now we are in the stage 2, that is the spectral analysis. Okay, so to do the spectral analysis, what we are doing is that first we need to apply the Hamming window. Okay, that means the speech signal is multiplied with the window characteristics. Okay, because we are interested in only one frame. Okay, because when you want to apply the DFT, I keep on telling the same point in the previous units also. So when you want to apply the DFT or FFT, in order to convert that from time domain to the frequency domain, the input should be stationary. But we are giving the input as a speech signal. The speech signal is a not stationary. Okay, it's a quasi-stationary signal. That means if you want to make that as a stationary, what we are doing is that we are considering only a very short segmentation of the speed, that is 10 to 20 milliseconds of the band. Okay, so we are considering that portion as its stationary. Then we are applying to the Fourier transform, and we'll be getting the spectral analysis, and we'll be having the Bach scale subbands. So the Fourier transform direct filter bank amplitude will be getting at the output. So this is the way you can see. So after doing the first frame, after first Hamming window and the second Hamming window, the portion, we are using the overlap method. So we are taking the first step, when you refer the previous. So this is the first Hamming window we have applied, and from here we have taken the second. By that means we are using exactly 50% of the overlap. this way, and you'll be getting another short segmentation. You're applying DFT this way. So you'll be getting the DFT of a signal chunk after manipulation.
Here, the input speech sentence is which is your native place. So, WN indicates the number of words in the input sentence, WD the number of words deleted, and WI the number of words inserted wrongly. And since no word is deleted or inserted, the word recognition rate is 100%. The following 3 slides demonstrate the result of speech recognition for different sentences.
Alright, so I hope you listen the words of a speaker. The results of the speech recognition they have got like this. So now we need to do the evaluation process, that is word error rate. We need to evaluate the performance measure. So this kind of things we need to observe. So the speech input sentence is the which is your native place, but the recognized text sentence which is your native place. There is no ambiguity at all. Whatever the words which are spoken by the speaker, the ASR has understood, and the same thing that we are getting as a text format. Okay, so in this example the word error rate are 0. Okay, but how we are calculating? So the WN is nothing but the total words in a original sentence, that is 5. WD, which are nothing but the words deleted in the recognized sentence. We have not deleted anything, and even if we have not inserted also, that is WI also 0. Now WER is given by the formula like this: WD plus WI by WN. We'll be getting 0. That means there is no error that is happening. Okay, so if you want to calculate the word recognition rate, 1 minus the previous answer, and we'll be getting 1. This is 100% accuracy we'll be getting. Okay, that is what. Next, let us see the second example. So this is the second example. The speech input sentence is I want vegetarian food. I want vegetarian food. Here also there is no ambiguity, the same as the previous example. Now let us concentrate on the next example. So here the speech input sentence is give me some discount, but the recognized text sentence give me some discount. Okay, these two words are inserted wrongly. How many words inserted? 2. So WN is 4. Okay, 1, 2, 3, 4, and then WD is 0, WI equal to 2, and we'll be getting this 0.5. That means 50% of the accuracy. And similarly, example number 4. Okay, you can easily understand what will happen.
The summary of overall speech recognition results is shown in the table for 20 sentences. The sentences in the recognized sentence column consisting red colored words indicates either number of words which are deleted or inserted.
Alright, so these are the some of the examples the author has taken. So we need to tabulate all the results of the 20 sentences the author has taken, and we are calculating how many words are inserted, how many words are deleted, and what is the actual portion that we are taking. This is what.
Finally, these two graphs shows the accuracy result of the speech recognition system. In WRR graph, that is the word recognition rate, as the graph approaches towards 1, the accuracy goes on increasing, and in WER, that is word error rate, as the graph approaches towards 0, the accuracy goes on increasing. So the WER and WRR are the parameters to decide the accuracy of speech recognition.
Alright, so these two important parameters we can easily conclude from the graph that is showing on the slide. So this is the word recognition rate, and this is word error rate. Okay, so closer the WRR to 1, higher the accuracy of the speech recognition module, and closer the WR to 0, higher the accuracy of the speech recognition. You can easily understand there are total 20 sentences they have taken. Thank you, student. Thank you for watching this video.